please go ahead.
Okay, good morning to all of you. I have not so slight flu, so this might go wrong in some time, in some point of the time, and that's the reason why I don't want to spoil your morning by seeing how bad I look at the moment. But now to the business. Explainable artificial intelligence. The first question is, what is artificial intelligence? There are multiple different definitions for that. Usually they are technologically agnostic and just generic definitions on what the AI should be able to do, much human performance in some intelligent way. And then there is also term machine learning. Those are not quite the same, but close enough for this presentation. But even bigger question is, what is explanation? Is it explanation if we have long equations on how the backpropagation works? Do you understand what actually is happening when a computer says that this is image of cat? Can you explain it, why it is an image of cat to the decision maker with this backpropagation algorithms and stuff like that? Most of us would say no. There might be some extremely talented individuals who would understand this long form of mathematics. But we have some simpler models which are self-explanatory, like a random, like a decision tree. And there's also term interpretable AI. Some of people use it as a synonym for explainable AI. But here there will be some difference between those terms. And then we have different kind of AIs. Some are supervised learning, and there are multiple different models here. This is the where the training data has also the labels of inside in it, so that the training happens in a supervised way. And then there's unsupervised learning, where we cluster or decompose stuff according to the data without labels. And also we have reinforcement learning, like Q-learning, where we give rewards to the system when it performs correctly. And for different types of explanations, we have local ones, which are valid only in the local neighborhood, and global ones, which should be valid for all of the material in every area of the model. But there's also instance explanations which are limited to the exact instance why in this case the results are what they are. And these explanations can be ad hoc, which are built into the model, which is the better case than the post hoc, where there are just extensions of the model. One question is why we need to explain the decisions of the artificial intelligence. One of the major reasons is ethical reasons. People have a right to know what is happening and why. This gives empowerment to the user. They know the reasons why the computer has decided something, and they can act on those reasons. And of course, informed consent. We need to have information to give consent to anything. Then there are legal reasons. In USA, in debt credit situation, there has to be specific reason given. In EU, we have GDPR, which has some demands for explanations. In France, there are laws which require explanation in intelligible form. Another reason is catching the errors. There has been quite many situations where the AI has done errors, and these have been only catched after the AI has been deployed into the wild. And these can be catched with proper explanations before deploying the AI. One reason is trust. Would you trust something which even the creator cannot explain? If you are betting your life on it, like in medical devices, or in a car, which is self-driven. And explanations give us traceability. We can trace where the decision went wrong, and then we can fix it in the next iteration of the model. And as I said, interpretable models are a bit different than explainable. Those are the models which are directly interpretable or ad hoc models. We can say exactly the reason why it has been given the result which we have gotten. Here we can start with linear regression. It's a simple form of AI in itself. We can exactly say why the line is here and why we are given the decisions according to the line. Next step from that is logistic regression, which still should be familiar from the statistics courses. And generalized linear models, this should be familiar to almost all of us. General additive models are something which I only found when making this presentation. If I understood correctly, the model is a combination of different functions with inputs of the decision variables. And of course, decision trees, we can explain why we end up here or here. Then we have rules learning. If glucose is higher than this, then we have 78 or 77% probability for the diabetes and stuff like that, and more rules after that. And co-nearest classification is also a self-explanatory model. And this should be familiar to all of us. And one new thing for me was multiple instance learning, which can be thought as a model. We sliced, for example, a picture to small squares and interpret all of them individually, and we find, for example, COVID in this pixel, this pixel, and this pixel. Then we can somewhat say that due to these pixels, we have COVID here, or let's say megapixels actually here. Also, model performance measurements are some sort of explanations for the model. For the goodness of it, we have a root mean square and normalized version of it, median absolute deviation, and Pearson's statistics. These are important for the user to know or actually the person who approves the model to the production to know that how well it performs. And for the goodness of prediction, we have predicted sum of squares, cross-validated R square, or coefficient of prediction, accuracy, and precision, and stuff like that with the selected top threshold. We have recall, F1 statistic, which is more or less joint precision and recall if you don't remember or recall that. Specificity, which is gives how well we find true negatives. Lift is the comparison between the model and baseline. Receiver operation characteristic curve, which is sensitivity as a function of -1. Actually, I think I have a typo in my notes here, and the area under the curve here. I hope that these are familiar to you. And now we are going to the actual different explanation models. I decided to start with the ceteris paribus profiles and partial dependence profile, which is also called individual conditional expectation. And these are both instance and global level. The ceteris paribus profiles are instance level explanation, and partial dependence profile is global level explanation. In the ceteris paribus profile, we are looking for what is the importance of each variable in this case. For example, how important is the age for Mary and John for their survival from the Titanic? And here we have fixed everything else except the variable in the question. And from that, we can get the profiles that for John, the fact that his deck crew has a lot of importance. And we can calculate oscillations of these profiles, and we can see the importance of the variables based on the total effect. Unfortunately, this was not implemented in the Python version of the DLX library. And the partial dependence profiles are the average importance of each variable. Here is all of the partial the graphs which I ceteris paribus graphs which I mentioned before, and their average on each case. And of course, this can be divided to the sub sets, and we can make a different profile of the for the age for the females or males, or by any other variable. And issues with this is CP and PD profiles is that they are not able to handle correlations of the variables, and they are not able to handle interactions between variables. Number of variables leads to high number of variables leads to high number of plots, and nominal categories are not handled well, and oscillations do not sum up to the instance predictions. And next step from these are local dependence and accumulated local profiles or effects. For the local dependence profiles, we have there are also about average importance of each variable, but here the data is taken only from those data instances which are close to the point where we are calculating the importance of the variable. This still leaves some more ways of improvement, which is in the accumulated local profiles. Here we only take a small window close to the point of interest with regarding to the value of that variable only. Here we can remove the correlations between variables. As you can see, the importance of the age decreased quite a lot here because it has lots of correlations with other variables in the case of the survival from the Titanic. And here we have some issues. The local dependence doesn't handle correlations. These don't handle interactions properly either. And we have to decide those breakpoints where we cut the data for these profiles. Then we have feature interactions. These are there are some implementations for measuring the interactions between variables. For example, age statistics, which can be found in this reference, and I couldn't find any implementations for Python for now. They have issues with computationally expenses, and they use random sampling, which can be unstable. And if there are exceptionally strong correlations, those will lead to some problems. Then we have functional decomposition. Here, the model is described as a sum of different functions with regarding to the decision variables. But here we don't have any idea what those functions are, and we have to just make a trial and error more or less. And if there are interactions between variables, then there's exponential growth of the number of features and functions. So this might be dead end if the model is even moderately hard. Permutation feature importance is measurement of the variable importance, and here we calculate model after permuting a feature. Large increase on the error means that the feature is important. This would need labeled data. This is also a random process which leads variations on the results. This can be biased by unrealistic data, and this still has some issues with correlations. And we have residual diagnostic plots, which should be familiar from the statistics. This is only for diagnosis of the finding for the finding areas with issues. This doesn't provide any explanations, but it's still useful to use in some cases. And next, we are trying to find a global surrogate. Here we try to make a model of the model, which interpretable model. So we are making a model of a model. There's inherent differences between them and even more about the reality. Why shouldn't we use the interpretable? Sorry, I have flu and my brain is fogging up. Interpretable model or something like that. Next method is prototypes and criticism. This is a way of generating prototype points which are representative of the normal data, and then selecting criticism points which is not represented well by the prototypes. This mainly helps us to understand the data, and if we have enough prototypes, we could make a model using those closest prototypes. And after we find the points and train a normal model, and we compare the predictions to correct values, we have some sort of analysis of the model. Here, the main issues are selecting the correct number of points and how to select the correct parameters for those models. One of the simple ways for the instance explanation is breakdown plots. Here we calculate the breakdown value as a difference between the mean of predictions so far and mean of the prediction with the added variable. So in Titanic, we have about 34% probability to survive. With males, it drops to a little over 20%. But if we add the first class here, then we increase our chances of survival a lot, and so far. But as you can see, the importance of the variables is different if we calculate this in a different order. And the sum is the final prediction, of course, in both cases. And there's also interaction version of it, where the fare, in this case, the cost of the ticket and the class of the ticket is highly correlated. So these are used as single variable. And from here, we still see that the prediction is at the end is the same, but reasons for that is different. And that order of the selection of the variables affects the results is a big issue with these breakdown plots. And interaction handling is computationally expensive. And if there are errors in the interactions which are so chosen to be used, then there will be some errors in the explanations. One of the popular models is local surrogates. This is the version where we generate a local interpretable model in the local neighborhood based on the results given by the black box model. And this can also be used for images. Here you can see a picture of cat and mouse, which is recognized as an American black bear with Inception version 3. Here the model is generated by variations of the data, and for the beer, these pixels were important according to the Lime model. And here we can see that these red pixels said that it should not be bear, but those are not influential enough. There in Lime we have some trouble with categorical and continuous variables, and this is model of a model yet again. So there's inherent error here, and slight change in a local neighborhood can cause large effects in the predictions. And with those, Lime can be manipulated. So it doesn't have so much, we cannot trust it as much as some other models. Then there is a way of generating counterfactual explanations. This is in here we try to find the decision boundary by generating a new instance for predictions, and thus find the importance levels of each variable. And here we can have multiple different counterfactual explanations for a single data point. Scoped rules or anchors is generating if-then rules for a decision border. And here we also have issues with parameter selection, discretization, and this can be exceptionally heavy for computations, and we actually don't know how well does it cover the model. And Shapley values are quite old technique, which are average marginal contributions of feature across all possible coalitions, which is more or less average of PD plots in all possible orders. And SHAP is a method for calculating approximate Shapley values for predictive models. So there's a minor difference between these because this is an approximate of the Shapley values. And these are computationally expensive and can be misinterpreted. And Shapley values itself uses all features, and this cannot give any predictions, only use those defined points which we have already. And the SHAP values only work if the model is additive, and these also can be manipulated. And for neural network interpretation, we have different ways of doing that. We can try to find the learned features, by deciphering what features the CNN finds, for example, in images. Here are a few links for those. And one of those actually states that we actually don't completely understand what we are doing and how well those how well this actually works. So are the results interpretable or not? And there's also issue that there are a high number of outputs. One of the major ways of explaining image related AI is this pixel attribution or saliency maps. And here we have the images which have been analyzed using pre-trained models and recognized with these pixels being important, or with slightly different algorithm, these pixels were important for the same model. Or maybe it was these areas, or maybe these pixels. So which of those explanations was correct one? As you saw, this is more or less unreliable and extremely fragile. One interesting way of explanation is concept detection. Here we try to interpret the neural network's inner state via concepts. How sensitive identifying zebra is to the concept of stripes. There's a Python library which calculates, which is tcav, and here we, in this case, I calculated the importance of host DST host in the connecting this the connections on the port, more than one or less than one importance is in detection of network intrusions from KDD 99 data sets. And the importance of these variables in the first dense layer number 0 or dense layer number 1. And both of them seem to be important. This has bad performance on the shallow NN and requires annotations on the data. And one interesting thing was that I was using a tutorial and with copy paste, and the tutorial had different results for one of those stuff. One way of analyzing neural networks is adversarial examples. These all three on the right are ostriches according to the neural network. So here we can find problems, but not explanations. One way of giving explanations is we are looking for influential instances. One way of doing this is deletion diagnostics, where we find data points which have high influence on the model, and we remove one and retrain the model and look what kind of difference it made. This is usable for debugging and understanding the behavior of the model. But there's a shortcut with influence functions, which are a statistical tool to calculate influence of a single point without retraining the model by use of the loss functions. This gives some understanding on the model behavior and finds most influential factors if the model doesn't perform with the test set as well as the training set. If we do this with those test set instances which are not predicted correctly. Here we have issues with the constant retraining, which is extremely computationally expensive, as you know. And we have no clear cutoff on how many points we need to select to have results, and the results are always only approximate ones. And there has been lots of criticism towards this explainable machine learning. As you saw, there are lots of issues with all of the explanation models. Making a model of model, is this really useful? Why we don't make why don't we use the interpretable model from the starting point? And we have multiple points of failures in these models of the models. And I found lots of resources for learning more about explainable AI. For example, in O'Reilly library, we have about 300 different results for these, which one can read or listen. In Google Scholar, I found 72,000 papers, and these two books, which are free, were my main sources for this presentation. And there is quite a many libraries for explainable AI, and I would say that there's moral issue that there are too many libraries which are doing the same thing, more or less. And as I said, I use these two books as the main sources. And for the multiple instance learning, I use this paper. And then here are the libraries which are used for generating the examples. And thank you so far. And I don't have any idea what time is it and how long I spent here.
Thank you, Tuomo. It is 4 minutes to 11, so you were really fast.
I was planning to show those Jupyter notebooks after this presentation, but those don't have any comments yet.
So do you have any questions or comments to Tuomo? Please go ahead.
I have a question.
Please.
I want to understand what is your opinion about this explainable AI? Is it a good idea, or do you agree with this point of view that it's in general not so good to use explainable AI? So maybe some comment on this.
I would say that it has been fluctuating during my time making this presentation. It's an absolute necessity to have explanations, and explanations don't work.
Okay.
So there's lots of work to be done in this area. There are some good ways of making explanations. Those are usually computationally hard, and but I would say that they have to be done in cases where the stakes are high.
Okay. So you would say let's work on the high quality explanation methods that are expensive.
If we need high quality explanations, if we only need to know this model works about like this, and no one's life is depending on it, then we can use something more simpler. And if the explanation's only for the internal use, then we can trust those explanations which can be manipulated.
Yes, and maybe somebody is aware of these manipulation possibilities, like an analyst, and he's not the decision maker, but somebody who gives advice can take this into account. Yeah. So it might be also good to have different explanations for somebody who is knowledgeable about explanations and somebody who is not.
Yeah.
Thank you. Any further comments?
One more question is the causal models. I want to understand, did you consider causal models? There are some techniques to find causal relationships.
Those were not presented on those two books which I used as a main source, and I have heard a little bit about causal models. Actually, I listened on YouTube a 3-hour-long YouTube video about causal salad. I think that you know that video. That I listened it. Was it 2 weeks ago? And so I haven't had time to dig into those yet properly.
Okay. Thank you.
Thank you. Any further thoughts, comments, questions?
I have a question.
Please.
Tuomo, are you planning to apply explainable AI in multi-objective optimization? I think so. So how do you plan? What's your plan in this direction? From perspectives, would you would like to use explainable AI? I mean, which?
I would say that the surrogate models are some sort of AI by themselves, and we should be able to explain those and find. And some of these explanation models give us more information about their behavior.
Okay, thanks.
And in many cases, we can use those
Interpretable, let me help you.
Models directly.
Thank you. Any further comments or questions to Tuomo? Oh, so
one last comment.
Yeah, please.
One last comment from me. I spent some 3 hours fighting with those libraries which I installed yesterday for those graphs and results. There are way too many libraries which are not compatible with each other.
So a lot of nuisance in practice.
What language? Python?
Everything here was done with Python.
Okay.
R has more comprehensive libraries for these. For Julia, I know that there are some libraries, but I don't know at all how good those are and how comprehensive those are.
Thank you. Any further thoughts to share?
Most of those which were left without any graphics had some sort of R library available, but not Python.
Okay. So thank you so much, Tuomo. As we have seen in recent times, this explainable artificial intelligence has been attracting more and more interest. So it has become more of a buzzword than AI itself. But it is not free of problems, as you said, and a lot of work to be done. And also there's a potential of applying explanations or interpretations in various contexts, but everything has to be done with utmost care. And we need to follow what kind of developments there are in the field itself, but also think of the ways that we could make the most of this in the meaningful way. Michael, did you want to comment something, please? Go.
Yes, I want to ask Tuomo, you spent a lot of time in working your way through the AI, and I was very impressed by the number of results you could summarize in one talk. I would like to ask you if you can share, because I'm working in my fellowship on XAI for multi-objective optimization, and it would be nice to share some experience on how to use libraries and so on in the future. Yeah, just it's more like a comment. And I really liked this presentation, so many techniques in one talk and also critical review of them. Just a comment.
Thank you.
Thank you. I would like to have an opinion on this, that should I make a new recording for the YouTube after I have less brain fog in me?
I don't see any need as such. But now that you mentioned, maybe we could stop the recording